Our first presentation today is about the RELY project, which stands for Reliable Reinforcement Learning for Sustainable Energy Systems. The speaker is Carlotta Sophie Freien von Tubeuf from the Technical University of Vienna. And as Florian mentioned, after the presentation, we will have some time for questions and discussion. So Carlotta, please, the stage is yours.
Yeah, thank you for the introduction. I said my name is Carlotta Tubeuf, although Sophie Freien von is not super necessary. And I'm a researcher from TU Wien, from the same research group as Florian. And I did my PhD on reinforcement learning for real-time control in pumped hydropower energy storage. So as it is not exactly industrial energy systems, but this method can be applied to also industrial energy systems, and B, I'm in the group of industrial energy systems. I thought this fits quite well, and I'm interested in your approaches to digitalization and using of artificial intelligence, where my research really falls into detail. So basically, the motivation for my PhD project and for a RELY project is that volatile renewable energy sources are being increased dramatically in the future, or even already currently. But a challenge for the electricity grid is that the stability needs to be guaranteed at all times. And one way to provide this flexibility and stability is by pumped storage power plants through generating energy by releasing water from the upper reservoir to the lower reservoir, or storing energy by pumping water from the lower to the upper reservoir. And we can provide this energy storage and generation. But in the future, when we have to operate these systems more often a day and way more flexibly, the flexibility needs to be increased of pumped storage power plants. And one way to do that, or what we need for that, is an advanced control strategy to enable precise and automated operation, in this case of pumped hydropower. And our approach is to use reinforcement learning for the real-time optimization in dynamic environments such as hydropower. But to begin with, what even is reinforcement learning, so that we can all get to the main ground. And then I will go on with how we're going to use, or how did we use reinforcement learning, and what were our first results in our project. So basically, reinforcement learning is one type of machine learning next to supervised and unsupervised learning, where a neural net learns from static data sets, and these types are very much used for predictive maintenance and analytics, for classifications and diagnostics. And reinforcement learning, on the other hand, learns not from a data set. It can learn from data, but not from a static set, but through the interaction with an environment. And this was brought up by mainly gaming, where we had a huge leap in the research of reinforcement learning a few years ago. And now it is gaining more and more attention also in other fields, and especially also in process control, so where we used it. But how does it work, reinforcement learning? Basically, we have this concept of an agent that interacts with the environment. So the agent, which is the brain, the neural net, like the thinking thing behind it, the agent takes an action that leads to a change in the environment, and then this new changed state gets fed back to the agent again, and it takes a new action. And together with the state, we get a scalar reward signal that gives the agent an idea of how good or bad was this action now in the environment. Ultimately, the agent defines a policy, and this policy tells the agent how to behave in a given situation. So if I'm in state A, let's do action B. If I'm in state C, let's do action B also, whatever. So you can imagine a bit like a grid. State this, do this action. And the goal is to find the optimal policy so that we maximize the cumulative reward overall that we get through the direction, to the moving in this environment, so that we can have the optimal solution. But to find this optimal solution, the agent needs to explore all the different state spaces that are possible in this environment. So taking a lot of random actions to find out, do I get to my ultimate goal? Do I maximize my reward or not? And also this formulation of the reward function can be quite tricky to, on the one hand, tell the agent, okay, where do we want to go? Or like what is a good outcome that we have, but on the other hand, not telling him too much of what our knowledge is, because we want to see also if the agent may also find a viable path that we didn't think of in the first hand. So in our case, the environment would be our pump storage power plant, and the agent tries to operate different processes, open different valves and so on. I'm going to get to that later. And then find out how can we get to our ultimate goal of accelerating the start and stop processes, so increasing the flexibility. But if you want to do that, if you want to use reinforcement learning in real safety critical environments like hydropower, there are some challenges. One, the training can take thousands of training runs to find the optimal strategy. So it can take ages for the agent to even find a path. And also, as I said, the algorithm during training may not only take viable actions, so we also have possible safety hazards when controlling an actual energy system. So this is why we would pre-train the reinforcement learning agent on a simulation model of the real-world power plant. And this is our concept for our project. Also, we have this reinforcement learning agent where we first pre-train on the simulation model, then transfer it to a lab scale pump turbine, and then in the future transfer the already trained agent to the real pumped hydro storage system. So the goal for our project was to develop a method for reliable and robust reinforcement learning and for safe testing of the control policy in a lab environment. And therefore we had, as I already said, this project RELY that was funded also by the FFG and the call AI for Green. We had project partners from around the whole spectrum of our main goals. So we had experts from machine learning, from the mathematicians at TU Wien, us as experts in energy systems, and also digital twins and simulating and modeling of energy systems. We had Evon, an automation software provider that helped us with establishing the connection between the reinforcement learning agent and the pump turbine in the lab. Then we had experts from the energy systems themselves, so the Tyrolean hydropower company, where we have the pump storage power plant that was the main model for how we then did our simulation on. So their real world power plant Kütai 1, I don't know if you know it, was the preprint for our model then. And experts also from how to disseminate all of this to other energy systems as well, the VGBE from Germany. Good. So the main concept that we developed and that we then also tested out was that we had first, as I said, the offline pre-training on the simulation model, and then to be safe so that we can also have a reliable deployment from the reinforcement learning agent that was trained online to the offline to the online control. We had a step in between, which was where we transferred the learned policy from the simulation to a rule-based control system. So we looked at what did the agent do in the simulation model. We abstracted this into a rule-based control, then operated this at the real test rig, and only after we found out that, okay, what the agent found out is actually doable, we let the agent really online control the whole energy generating unit. And this was then the sim to real transfer from the simulation to reality. And I'm gonna present now the results for each of these steps. The simulation environment that we used was, as I said, the representation of the pump turbine test rig at TU Wien, which again represented the real-world power plant from the TVAC, Tyrolean Hydropower Company. It was modeled in MATLAB Simulink using the language Simscape, and we based our model on the pumping quadrant for the pump turbine test rig. So as I said, a pump turbine can theoretically be used in pumping mode and in turbining mode, but for our first use case, we used only the pumping. So the pump startup of a pump storage power plant was our first use case. This is that we are from a standstill. So you can see here the phase, or like the sketch of a typical pump turbine unit. And during pumping, we have the water coming from the tailwater vessel being pumped to the headwater. And this here is the pump turbine, the runner, that rotates and therefore establishes pressure that pushes the water from the tailwater to the headwater. And for the pump startup, that we want to accelerate, so we want to be quicker in being able to store energy from the grid. This was our first use case for the reinforcement learning agent. So the agent needs some information from the environment. These were the states. So we gave it all relevant states for that it needs to know to be able to categorize or characterize the current state. So as all the valve positions, the flow rate that is currently there, the torque of the shaft here, then and so on. And then it had 4 different actions that it could take at all times. First of all, it could open or close this huge ball valve that prevents the flow from the headwater to the tailwater. So if this is closed, no water can flow through, and this needs to be opened to be able to pump water up. Then the second one was here this air injection valve. So what I didn't mention is that theoretically, when you're doing a pump startup and pump storage power plants, as they can rotate in both directions to either store energy or pump water up. When we go into the pumping mode, the whole turbine first needs to be dewatered. So usually we have water in this runner, but for pumping we need to blow down the water. So we need to inject air. Then the water gets dissipated into the tailwater, like back to the tailwater. Then we start connecting to the grid, start the acceleration of the shaft and therefore of the runner. And only when we have reached the synchronization speed, we synchronize with the grid, and then we have the correct speed so that we can run water again so we can let the water again into the runner so that we can pump this water up. This is necessary because otherwise we need a lot more torque and therefore a lot more power to get to this to the synchronization speed. And typically the storage units that we look at have a starting motor for accelerating the pump turbine in this direction, and they do not have enough power to accelerate when the runner is full with water. Okay, I hope you could follow me. So basically, this is the conventional approach how you do a pump startup. First, you have everything closed from a standstill. You open this air valve. You want to blow down the runner. Then you accelerate the pump turbine until the synchronization speed is reached. Then you synchronize with the grid, close the air valve again, open this huge ball valve, open also the guide vanes that are responsible for the flow rate. And then as soon as the target flow rate is reached, the pump operation can start. And this process, this conventional pump startup process, was our baseline for what we want to see. Can the reinforcement learning agent achieve also a control of the same process, or would it find something different? How could it find something different? We gave it a reward function, and based on this reward function, the agent wanted to maximize. And to incorporate everything that is relevant for how to operate a pump turbine, we have several terms in this reward function. On the one hand, we want to have a reward for when the agent is able, or when we have a flow rate reached or target flow rate reached, and then a penalty proportional to a deviation of the flow rate. We have a penalty for the startup power. So if the startup motor needs to has a lot of power, we need to buy it from we need to pay for the electricity that is needed to accelerate. So this is a direct penalty. Also penalty if we use too much air, and also costs for the air compressor to compress the air that is needed for blowing into the runner. Also some wear-related penalties we included, and for a penalty for valve actuations, because you can imagine the reinforcement learning agent doesn't know how to typically operate. But so it is possible, or what happened was actually that it was like, okay, open, close, open, close, open, close, just to see what happens. But in reality, this would not be very smart to do. So this is why we had to include also a penalty for valve actuations. And you see this iterative process of how we approached also this whole concept of reinforcement learning for any case, actually. Then also a termination penalty if the agent did not reach the target of pumping operation in the end, but also a reward if the mission succeeded. And then overall, all of this comes together in a cumulative episode reward, and this was being maximized. Therefore, we used a PPO agent, a proximal policy optimization agent, in Python, and connected it via a TCP/IP communication to MATLAB, to our simulation model in MATLAB. And here you can see the training reward over the training episodes. So you see in the beginning we have a quite bad reward, but quite quickly we reach the agent converges to an optimum. The black dotted line that you can see here was the reward that is achieved when using the conventional policy that I showed you earlier. And we can see that the agent even reached an even higher reward than that. So the dark blue line is the average reward that we have in the end. And when we compare the two, the conventional strategy and the reinforcement learning strategy, we can see that the startup duration was way faster. So we the main benefit, or like the main reason why our PPO reward was higher than the conventional policy reward, is that we managed to synchronize earlier and to have the pump operation achieved earlier than with the conventional strategy. We also used less air in simulation, that you can see here, and that the cumulative reward overall was higher for the reinforcement learning strategy. So what was different in this reinforcement learning control strategy? As you saw before, in the conventional approach, we have a very sequential process of pumping, or like of getting to pump operation, and the reinforcement learning agent decided to do a lot more simultaneously, what you probably wouldn't do in the first thought. So it decided to, while opening the valve, immediately accelerating the pump turbine. This would use more power on the startup motor, but as it accelerates quite quickly, you can still reduce the startup torque with blowing in air. And then as soon as half of the synchronization speed was reached, also the ball valve was immediately opened, so that we can have a flow target flow rate reached way earlier. This was very, for us, this was very insightful. We also talked to the operators that we had in our project with, and they were very hesitant in doing so, because that is not something that they ever did before. The reinforcement learning agent learned that from the training and the simulation model, and we were also hesitant, can we even do that? Are there not some limits, physical limits, that we didn't incorporate in our simulation model that will come into play later on? So this was very, a big question mark for us. So we decided, okay, we want to try it in our lab, but we will, as I already mentioned, we will do it in a rule-based manner before. So we translated this whole sequence into if A happens, then do B, before we let the agent control it online. So we tested it in our lab scale pump turbine. Therefore, we had this control system by the automation software provider that was in our project, and we connected it via MQTT. We had the control of our pump turbine in the lab. And just quickly, we saw that the rule-based control, so the reinforcement learning strategy translated into rule-based control, did work. So we were a bit hesitant if maybe the torque is too big in the beginning, which it was not, or that maybe we cannot establish the discharge, or like the discharge is the same as the flow rate. But basically, the experiments in our lab just confirmed what we saw in the simulation. So there we were quite happy that it still worked and that we have the higher reward. But then we tried for the online control, and there we can see some deviations. So while it still opened the ball valve at the same time, we also have discharge established, and we have the speed coming to the synchronized speed here, as fast as with the rule-based approach. But we cannot, like what the agent didn't manage is to achieve the desired flow rate here. And this is because the measurement signals that the agent got via MQTT were still a bit deviating from what it saw in simulation. And this is a problem, I guess, that you all know from like digitalization projects, that the reality then in the end is still a bit different than it was in the simulation. However, we were still quite happy with the results that we got a discharge, and that we are now able to work on deviations in the simulation model, also sensor signals that are like the latencies in our signals are maybe too long for some signals, for some sensors. So we will work on that in the future. Overall, when we discuss the policy, so the leftist one is the conventional control policy, in the middle the abstracted rule-based reinforcement learning strategy, and then the online reinforcement learning strategy. We didn't manage to achieve the pumping operation, so we don't have a pump startup duration for the reinforcement learning, but the time until synchronized, the synchronization with the grid was successful and also faster for both reinforcement learning approaches than with the conventional approach. We used a lot more power on the startup motor, so maybe this would not be possible in reality. Because in our lab environment, it was possible to have a lot more power for the startup motor than would be in reality. But we will work on this. And the air used was also significantly lower for the reinforcement for the online control than for the rule-based control. And these deviations you see are mainly arising from like signal discrepancies between simulation and reality. Yeah, to conclude, in our project, we did the first experimental demonstration of a reinforcement learning-based control system for pump startup in a reversible pump turbine. So in general, in hydropower, reinforcement learning is very much like research on that and on controlling processes is very much in the beginning. And we are quite proud of what we did even in the lab. We did integrate a digital twin platform for safe offline training and then validated implementation into a real world use case. But there were, as I said, some sim-to-real challenges due to sensor noises, signal delays, model deviations. However, our methodology demonstrates a practical approach to introducing reinforcement learning in safety-critical energy systems, and this must not only be hydropower, but also industrial energy systems. Yeah, so I would be interested to know more about your challenges in maybe you had some insights into reinforcement learning already also, or generally in how to bring something from the model to reality. And yeah, if you have any further questions, I'm very happy to answer them.
Yeah, thank you so much, Carlotta. That was a great overview of reinforcement learning. We now have approximately 5 minutes for questions and discussion. So if anyone in the audience have a question for Carlotta, then feel free to ask now.
I think the first one to raise the hand was Karim Nadim.
Yes. Hi, Carlotta. Thank you for the presentation. Very interesting. I have two quick questions, if you don't mind. First thing, you mentioned that you transformed the reinforcement learning policy into rules and rule-based. I think that's very interesting. I wanted to know how did you do that?
Basically, we looked in the final optimal policy at the simulation model, and we really sat down with experts and translated this into what I showed you also, this flow diagram. And then from this flow diagram, I just coded in Python, if this state is this, then do this action. And we controlled it basically via if A then B via MQTT. So we translated it for this specific use case. We could, if it would be a different use case, the reinforcement learning agent would probably control something, but this I probably could not translate directly into rule-based control.
Thank you. My second question, so I saw your reward function, you had a lot of constraints and you gave a lot of penalties, and of course this adds to the complexity of the reward function. I wonder, how did you do the weighting for these different penalties, because it's hard for the agent sometimes to learn different rewards and different constraints and penalties at the same time. Yeah.
I guess this was also probably the main timely research that we did, was this reward function. And what we did was we managed to monitorize every constraint, every penalty and reward that we had. So we tried to find economic factors for that. We talked to the experts from the industry and said, okay, approximately what would you say, or translated into power and then into electricity costs, so that we have this one domainer, or that we can even compare it with each other, so that everything was money. And this is how we put the weights on it. And this worked quite well, but in the end we even had to incorporate also what we called then feasibility constraints that we needed to implement as well. For example, this mission reward, where we just gave it a plus also if it achieved it. So we have these two groups. One, on the one hand, these technical parts of the reward function where the weights were, everything was monitorized, and then some feasibility parts of the reward function where we just added, to get what we wanted.
Thank you.
Okay, to stay on schedule, I would say we would take one more question. I think Amasus was the next one.
Yeah, thank you very much. Just curious about the integration of your online control with existing control systems. How, because this should coexist with PLCs or DC, stuff like that. What about safety interlock systems and so on? Do you see any challenges there, or in a real case?
Sure. I mean, what we did was we had this connection via MQTT to the automation system, but then in there we also spent some time with our lab professionals to have some extra safety regulations incorporated as well. So if, I don't know, some value or some pressure value goes above this, then immediately stop. The agent gets, the connection is being stopped, and you shut down, or you manually have to set a value or something. So this was something that we also integrated, and this is a huge challenge. Another challenge that I can see is being automated very soon. So, but for each use case, you have to sit down and see what are our risks, what do we need to incorporate, and then do that.
yeah, maybe use reinforcement learning for HAZOP for.
Yeah.
Thank you.
Thank you.